Here is the example problem. A process for methanol synthesis is shown here. The reactions involved are methane plus water forming carbon dioxide and hydrogen, methane plus water forming carbon monoxide and hydrogen, and carbon monoxide plus oxygen forming carbon dioxide, and carbon dioxide reacting with hydrogen to form methanol and water. So, these reactions are labeled as main reformer reaction, reformer side reaction, carbon monoxide converter reaction and methanol synthesis reaction. 10% excess steam based on the main reformer reaction is fed to the reformer, and the conversion of methane is 100% with a yield of 90% for CO2. Conversion in the methanol reactor is 55% on one pass through the reactor. The stoichiometric quantity of oxygen is fed to the CO converter, and the CO is completely converted to CO2. Additional makeup CO2 is then introduced to establish 3:1 ratio of hydrogen to carbon dioxide in the feed stream to the methanol reactor. Methanol reactor effluent is cooled to condense all the methanol and water, with the non-condensable gases being recycled to the methanol reactor feed. The hydrogen to carbon dioxide ratio in the recycle stream is also 3:1. Since the methane feed contains 1% nitrogen as impurity, a portion of the recycle stream is purged to prevent nitrogen accumulation in the system. The purge stream analyzes 5% nitrogen. For every 100 moles of impure methane feed, you are asked to calculate the moles of hydrogen lost in the purge, moles of makeup carbon dioxide required, recycle to purge ratio in moles per mole, and quantity in kilograms and composition of methanol solution produced. So, this problem covers all the aspects of chemical reactions with recycle and purge for a multi-unit system. Let us try to solve this problem. The problem statement gives us that 100 moles of impure methane is fed, which means stream 2 would contain 100 moles, which would be 99% methane and 1% nitrogen, giving us 99 moles of methane and 1 mole of nitrogen in stream 2. So, our basis would be 100 moles in stream 2. So, this contains 99 moles of methane and 1 mole of nitrogen. So, we have also been told that stream 1 is 10% excess water vapor which is being fed or steam which is being fed. So, we can calculate the requirement for water vapor based on the reformer reaction. The main reformer reaction was given as methane plus 2H2O gives CO2 plus 4H2. So, this means for every mole of methane fed, you require 2 moles of water vapor or steam. So, here 99 moles of methane is fed, which means 198 moles of steam is required. We know that 10% excess is actually fed. This implies 198 times 1.1 would be the actual number of moles fed in stream 1. So, this is 217.8 moles of water vapor being fed. So, stream 1 is 217.8 moles. Now, we need to calculate information about stream 3. For this reason, we will choose the reformer as the system and perform material balance calculations. So, we can write methane balance. We know that 100% of methane is consumed. So, which means methane consumed would be 99 moles. So, output methane in stream 3, which would be equal to input minus consumption, would be 0 moles. So, similarly, we can write component balances for carbon dioxide. So, carbon dioxide balance would be input minus output plus generation minus consumption equals accumulation. At steady state there will not be any accumulation. Carbon dioxide is a product, so it is only generated, there is no input of carbon dioxide. So, your output is actually equal to generation. We have been told that 90% of methane consumed produces carbon dioxide. So, we know 99 moles of methane was consumed. So, 90% of this was converted to carbon dioxide. So, number of moles of carbon dioxide produced would be 90 divided by 100 times 99. So, CO2 generated would be equal to 89.1 moles. So, this implies stream 3 contains 89.1 mole of CO2. Similar to carbon dioxide, we can also perform carbon monoxide balance, which would again be output equals generation. So, we knew that 90% of methane which was consumed went into main reformer reaction and the rest 10% went into side reformer reaction. This implies 9.9 moles of methane went into formation of carbon monoxide. Based on stoichiometry, this would have produced 9.9 moles of carbon monoxide. So, output would be equal to 9.9 moles of carbon monoxide. We can also write a balance equation for hydrogen. So, hydrogen is not coming in, it is only being generated. So, your output would again be equal to generation, but here you would have two generation terms from reaction 1 and reaction 2. Based on the stoichiometry, we know that for every mole of carbon dioxide produced, 4 moles of hydrogen is being produced. So, 89.1 times 4 would be the generation of hydrogen by the main reformer reaction. From the side reaction, you would have for every mole of carbon monoxide produced 3 moles of hydrogen being produced. This means 9.9 times 3 moles of hydrogen is being produced. So, the total output for hydrogen would be 386.1 moles. If we were to write a balance for water, we know that input minus output minus consumption would be equal to 0, because water is not generated as it is a reactant and accumulation would be 0 at steady state. Thereby, output is actually equal to input minus consumption. So, input is 217.8. Based on the stoichiometry, we know that for every mole of carbon dioxide produced, 2 moles of water was consumed. So, for 89.1 moles, you have 89.1 times 2 moles of water consumed. Similarly, for the side reaction, for every mole of carbon monoxide produced, 1 mole of water was consumed. So, 9.9 times 1 mole of water was consumed. So, output for water was 29.7 moles. As nitrogen does not take part in the reaction, output for nitrogen would be 1 mole. So, based on this, stream 3 composition would be as follows. Stream 3 contains carbon dioxide 89.1 moles, carbon monoxide 9.9 moles, hydrogen 386.1 mole, water 29.7 moles and nitrogen 1 mole. So, now we have performed the calculations for the first system. The next system of interest would be the CO converter. For the CO converter, we have been told that stoichiometric requirement of oxygen is fed and there is complete conversion of carbon monoxide to carbon dioxide. This implies the 9.9 moles of carbon monoxide gets converted to form 9.9 moles of carbon dioxide. So, if we were to write a carbon dioxide balance, we would have input plus generation equal to output. So, the output would be 89.1 plus 9.9 giving you 99 moles of CO2 leaving. So, stream 5 would have the same components as in stream 3 except for carbon dioxide being 99 moles instead of 89.1. So, this would be carbon dioxide being 99 moles, and you do not have any carbon monoxide here because it has all been converted. Hydrogen would be 386.1 moles, water would be 29.7 moles, and nitrogen is still not taking part in reaction. So, you have 1 mole of nitrogen leaving. The problem statement gives us that stream 7 contains hydrogen to carbon dioxide ratio of 3:1. The stream which is being mixed with stream 5, that is stream 6, is only CO2 makeup, which means all the hydrogen present in stream 7 has to come from stream 5. This implies stream 7 contains hydrogen as 386.1 moles. Knowing this, we can calculate total CO2 in stream 7 as 386.1 divided by 3, which is 128.7 moles. Now that we know 128.7 moles of CO2 is present, we can write a balance for the mixing point for CO2. The CO2 balance for mixing point would be input equals output. So, you have two inputs here. One input comes from stream 5, which contains 99 moles of carbon dioxide, and you have another input from the CO2 makeup stream, we will just call that I6, would be equal to the output, which we know is 128.7 moles. So, this implies CO2 makeup which is given would be equal to 29.7 moles. So, this is one of the values which we needed to calculate. So, stream 6 we have calculated to be the CO2 makeup of 29.7 moles. Based on this, we can also get the information on stream 7. The only component changing from stream 5 would be carbon dioxide, which is being added. So, we now have carbon dioxide of 128.7 moles and hydrogen would be 386.1 moles, and we have water as 29.7 moles, and nitrogen is still being present as 1 mole. We have also been asked to calculate the amount of hydrogen which is lost through the purge stream. Taking the overall system into account, the nitrogen which is entering through the methane feed would have to leave only through the purge stream. So, if we were to write a nitrogen balance, we would have input equals output, thereby our purge stream contains 1 mole of nitrogen. We also have one information about the purge stream, which is purge stream contains 5% nitrogen. This implies 1 mole accounts for 5%. So, total purge stream would be 1 divided by 0.05, which is 20 moles. So, we have 20 moles of purge being sent out of the system. Now that we have the total purge stream, we still need to calculate composition of the purge stream, and we also need to identify how much methanol is produced. For this reason, we will choose a different system. Let us choose this particular system, which has the mixing point for the recycle stream, the methanol reactor and the condenser. For this particular system of interest, we know that all the information about the stream 7 has been calculated, and purge stream we know the total purge, and we have some information about its composition also. Let us try to perform the material balances for this system. Based on what has been given to us in the problem, stream 11 contains methanol and water only, and stream 12 contains all the non condensable components. This means that stream 12 would contain all the non condensable components which are entering into the system. Those non condensable components would be unreacted hydrogen, carbon dioxide and nitrogen, which does not take part in the reaction. The problem statement also gives us that the recycle stream contains hydrogen and carbon dioxide in the ratio of 3:1. This means purge stream would also contain hydrogen and carbon dioxide at the ratio of 3:1. Using this, we can calculate the amount of hydrogen which is leaving through the purge stream. So, what we have here is hydrogen is to carbon dioxide in the purge stream is 3:1. This implies you have 1 mole of nitrogen, 3x moles of hydrogen and x moles of carbon dioxide in the purge stream. The total purge is calculated already as 20 moles. So, what we can do is 3x plus x plus 1, which is the total number of moles of the purge stream, is equal to 20, giving you x as 4.75 moles. So, the purge stream contains 4.75 moles of carbon dioxide, 1 mole of nitrogen and 14.25 moles of hydrogen. So, based on this, we have calculated 14.25 moles of hydrogen is being purged in this process. For the system chosen, we have a methanol reactor where hydrogen is being consumed. We can calculate hydrogen consumption based on the information we have about the input and output terms for hydrogen. Using this, we will be able to calculate how much methanol has been produced. Let us try and do this. So, if we were to write the balance equation for hydrogen for the system chosen, which is basically this, what you would have is input minus output is equal to consumption. We already know that input is 386.1, which is coming in through stream 7, and we calculated that the output was 14.25 from the purge stream. So, consumption is basically equal to the difference between the two, which is 371.85 moles. So, that is the total consumption of hydrogen in this system. Similarly, we can calculate the consumption for carbon dioxide if we write the carbon dioxide balance, which would be input minus output equals consumption again, and consumption would be 128.7 minus 4.75, giving you a value of 123.95 moles. Based on the stoichiometry, we know that for every mole of carbon dioxide consumed, we have 1 mole of methanol produced. This implies 123.95 moles of methanol would have been generated in this system. So, if we were to write a methanol balance for the system chosen, output would be equal to generation, which is 123.95 moles. So, from this equation we know that 123.95 moles of methanol was actually produced in this system. We have been asked to calculate the mass of methanol and the mass fraction of methanol in this stream 11. So, 123.95 moles of methanol is actually equal to 3966.4 kilograms of methanol. We also need to calculate the amount of water which is present in the stream, so that we can calculate the composition of stream 11. How much water would be present? For that, we need to perform the water balance equation. So, the balance equation would again be output equals generation plus input. So, using stoichiometry, generation would be equal to 123.95 moles of water being produced. We already know input is 29.7 moles coming in through stream 7. This means our output for water in stream 11 would be 123.95 plus 29.7, giving you a value of 153.65 moles. So, 153.65 moles of water is equivalent to 2765.7 grams of water. So, the total stream 11 mass would be 6.7321 kilograms. Mass percentage of methanol would be 3966.4 divided by 6732.1 times 100, giving you a value of 58.9%. So, stream 11 is basically 6.7321 kilograms of 58.9% methanol solution. For calculating the recycle stream, we would like to write a balance equation for either the mixing point or for the splitting point. The problem with the splitting point would be we would have only one independent balance equation. So, it is better to write the balance for the mixing point. So, for writing the balance for the mixing point, we would have to have information about stream 9. How do we get information about stream 9? We have been told that the single pass conversion for methanol production was 55% of carbon dioxide coming in. So, this means the amount of methanol which was being produced and removed from the system was based on 55% of carbon dioxide entering into the methanol reactor as the gross feed. So, what we have is 123.95 moles of methanol being produced. This implies 123.95 moles of carbon dioxide was consumed in this methanol reactor through a single pass. So, gross CO2 entering would be 123.95 divided by 0.55, giving you a value of 225.36 moles. As we know that the ratio of carbon dioxide to hydrogen is 1:3, gross hydrogen entering would be 3 times 225.36, giving a value of 676.09 moles. Now that we have information about the carbon dioxide and hydrogen which is present in the total feed, let us write the balance equations for the mixing point. The carbon dioxide balance would be input equals output. So, input is two streams, one is stream 7 and the other is stream 8, and output is from stream 9. We know that the output is 225.36 and the input in stream 7 is 128.7 and the rest would be the input in stream 8. So, this would be the CO2 input in stream 8. So, this would be CO2 in stream 8 can be calculated as 96.66 moles. Similarly, writing a balance equation for hydrogen, we would be able to calculate hydrogen in stream 8 as 289.99 moles. This is not sufficient because we still need to calculate the amount of nitrogen which is coming in through the recycle stream. We have one information about the nitrogen concentration which is 5%. So, we know that the total moles of recycle would contain hydrogen at 289.99 moles, carbon dioxide which is 96.66 moles plus whatever would be the moles of nitrogen which is basically 5% of the total moles, so which is 0.05 times x, and x is the total number of moles. Using this we can calculate the total number of moles which is recycled as 407 moles. So, the ratio of recycle to purge would be 407 to 20, which is 20.35. With this, we have performed all the required calculations and we come to the conclusion of today's lecture. In the next class, we will perform one more example where we consider a biochemical system with recycle. Until then, thank you and goodbye.